Hey guys, we are going to talk about limiting reactants now. Limiting reactants are those substances that run out first and stop the reaction. So a limiting reactant is what you run out of. Now, an example that I want to start with here is this idea that in the very beginning of a water formation reaction here, you've got two known amounts of your starting substances. We've got 10 moles of the hydrogen, and you got 7 moles of the oxygen. Okay, so that's represented visually down here as well. You can count them up and you can see, right, we've got 10 of our white molecules, we got 7 of our red molecules. Now what's going to take place is the reaction is going to use up as much as possible in order to get these to react. So if you think about these stepwise, it's like, oh, we're going to have that 10 and that 7 and 0, right? Those are our starting amounts of each thing. What I'll do is I'm going to break them down in the way that we lose them. So it's like I'm going to lose 2 of these at a time. So 10 minus 2, I'm going to lose 1 oxygen, minus 1, and I'm going to gain 2 on that. So doing incremental totals, I've got 8, I've got 6, I've got 2. Now we do it again, minus 2, minus 1, plus 2. We see what we get. 8 minus 2 is 6, 6 minus 1 is 5, 2 plus 2 is 4 now. Do it again. We're going to see that we get 6 minus 2 is 4, 5 minus 1 is 4, we got 4 plus 2 is 6. Keep doing it again, right? So just little by little, step by step, you can see we're going to eventually end up running out of something. And we find that it's going to be our hydrogen. You run out of hydrogen, you see that we have 2 moles of oxygen left. We see that it made a total of 10 moles. And that's what we see here as our after reaction amounts. So we didn't have the perfect amount so that both things run out. And in most cases, you won't have that. You're typically going to have something that you have in excess. So here, our oxygen is the excess reactant. And anytime that you're planning out an experiment, you want there to be something that definitely runs out and one thing that definitely does not run out. That way you can attribute the results of your data to one specific change. Now, we're going to work through our first sample here. We're going to find how much product is formed. In the Haber process, if you take a look at this, we're going to be forming ammonia, NH3, based on nitrogen reacting to hydrogen gas. So our question is, how many moles of NH3 could be formed from 3 moles nitrogen, 6 moles hydrogen? So what we've got to do is this. You got to think about it from 2 perspectives. You've got 3 moles of nitrogen. How much ammonia could that make? 6 moles of hydrogen. How much ammonia could that make? So I'm going to set this up basically as 2 problems to compare to each other. We've got the 3 moles of nitrogen that has to be converted into ammonia. And then we also have our 6 moles of hydrogen that have to be converted into moles of ammonia. So then I'll have moles and moles. I'll be able to compare how much ammonia is formed. So set up here, 3 moles of ammonia, looking at the reacting ratio, I want to get rid of moles of nitrogen to find moles of ammonia. We see that's 1 nitrogen for every 2 ammonia. So 2 here, 1 here, our moles cancel. We're going to see 3 times 2 gives us 6 moles of ammonia are possible. Not necessarily that's what can happen or what will happen, but that's what can happen. 6 moles could be made from nitrogen. So the possible from nitrogen is known. Now we've got to find the possible from hydrogen. We're going to start with our 6 moles of hydrogen. Now I want to cancel moles of hydrogen to find moles of ammonia. And we see that in that case, it's a 3-to-2 ratio. 3 hydrogen for every 2 ammonia. So 6 times 2, we get 12, divide 3. We're going to find that 4 moles of ammonia are possible from the hydrogen. So what we have to do at this point is do a comparison. I've got 6 versus 4. Whichever one is smaller, that identifies the thing that runs out. So because 4 is less than our 6, that tells us that hydrogen is the limiting reactant. Hydrogen will run out first because it can only make 4. After those 4 are made, Well, we're done. We're going to have excess nitrogen in this process, and we definitely know that we're going to run out of the hydrogen. So we've done the math already. We figured out that 4 moles of ammonia are possible, and that's our final answer. Okay? Now here's another example that we can work with. So we've been given this, this reaction, which again, it's formation of water, but in this case, it's water as a gas. Should be very comfortable with it by now. And we have a fuel cell that contains 150 grams of hydrogen and 1,500 grams of oxygen. So one thing to notice here is that whatever device we were measuring these with wasn't all that specific. We've only got 2 sig figs here and only got 2 sig figs here. So that's going to limit our final answer eventually. For now, we're just going to do calculations, assuming that we have more to work with. So the question is, how many grams of water can form? We're going to grams of water. So we're going to separate this into our 2 problems again. This time, you've got a larger series of steps, so let's just do them on top of each other here. You've got your 150 grams of the hydrogen. And the first series has to get rid of grams of hydrogen to find moles of hydrogen with our molar mass. That's 2 grams per mole. Then we want to get rid of moles of hydrogen to find the number of moles of water that can form. So looking at that, we have a 2-2 ratio, 2 moles hydrogen to 2 moles of H2O. Then we want to get rid of the moles of water to find the grams of water that are possible. Get 1 mole of water for every 18 grams. So doing the math on that, we're going to break it down and find that there are 1,350 grams of H2O possible from our hydrogen source. Okay, so that's the possibility from the hydrogen source. Next thing that we'll do is the same conversion setup, except beginning with oxygen. It's going to be 1,500 grams of oxygen. So our conversion steps, get rid of grams of oxygen to find moles of oxygen. That's going to be 16 is the molar mass of a single oxygen atom. In an oxygen molecule, you double that. So we've got 32 grams to 1 mole. Then we want to cancel our moles of oxygen out to find the moles of water possible. So this time it's going to be a 1-to-2 ratio, 1 mole of O2 for 2 moles of water. Now cancel your moles of water to find the grams of water. Once again, 18 grams per mole. We do the math on that, multiplying 1,500, divide 32 times 2 times 18, the ones we don't care about, right? And that gets us to 1,692 grams of H2O are possible from our oxygen source. Now doing comparison, we see 1,350 is smaller than 1,692, so that 1,692 can't happen. What we've learned is the hydrogen is limiting in this reaction. And we know that 1,350 grams of H2O is possible, but going back to our sig figs, we're going to then round that to 2 sig figs. That's going to be 1,400 grams of water when rounded. Now we're going to bring in the concept of theoretical and percentage yield. So the theoretical yield is what can happen. Theoretically, if all of our reactant particles found some way to come together with the right energy, right position, all those right things, then all of our potential product would happen. The theoretical is the amount that could form if that happens. Now the actual yield is always less than the theoretical. Okay, so just watch out for that. In reality, not all particles will successfully find their way to each other and combine to form a real reaction. So the actual yield will be less than the theoretical, which brings us to this concept of a percent yield. It's our ratio of how much product actually forms compared to the theoretical amount. So our percent yield formula, actual over theoretical times 100. If, for example, you had a calculation that says you're supposed to get 20 grams of product, but you do the experiment and you get 10 grams of product, When you set that up, you're going to find that 10 over 20 times 100 gives us 50% yield of that thing, only 50%. So let's practice some of these. Here in sample 320, we've been given this acid, adipic acid, H2C6H8O4. That's a fun one. We use it to produce nylon, and it is made commercially by a reaction between cyclohexane and oxygen. So we've been given our reaction equation, our balanced chemical equation set up, and this one's going to break up into a couple of parts. So the adipic acid, let's fix that one. The adipic acid is going to be formed using 25 grams of cyclohexane, and that is definitely going to be limiting. So that means we have excess oxygen in our process. Okay. Well, we set this problem up once again. Plan out. The goal is to go from our cyclohexane into adipic acid. So really, this is just a gram to gram problem. We've done these before. We'll just get it done again. 25.0 grams of the cyclohexane are C6H12. The first thing is cancel out your C6H12 to find the moles of C6H12. So getting rid of grams to find moles. For this, we're going to say it's what? 12 times 6 and 12 times 1. Add those together. I've got a molar mass. 84 grams comes out for me. So 84 grams. Now we want to cancel out your cyclohexane, moles, and go back into moles, but this time for our adipic acid. So that again is H2C6H8O4. Fun one to write out. And looking at it, we can see that we have a 2:2 ratio. Going to be nice and convenient to cancel. Now I have moles of the adipic acid, and I want to get grams of the adipic acid as a final point. So I'm going to combine all the numbers there. You got the hydrogen, there's a total of 10 hydrogens, so there's 10. You get 6 carbons, so 12 times 6, and then you've got 4 oxygens. I'm going to go 4 times the 16 on oxygen. We find that's 146 grams per mole on adipic acid. So just looking at it again, all of our cancellations check out. All the right substances go away. And when we put it together, we find that 43.5 grams of our adipic acid can theoretically be made in this process. That's again if 100% of all reactants came together perfectly. Now, question B is asking, if you were to obtain 33.5 grams of adipic acid in this process, what's our percentage yield? So this one should be, again, fairly straightforward. It's going to be the actual over the theoretical yield times 100. So we set that up, the actual 33.5 grams over the theoretical 43.5 grams times 100. We find that our final answer on that ends up being 77%. And life is good. So hopefully that was helpful. If you have additional questions, definitely make sure that you come talk to me, and you guys have